In this presentation, we'll cover the functional requirements and controller validation using simulations of a black start capability of HVAC connected offshore wind farms. My name is Ramon Blaso Gimenez, and I'm a professor with the Technical University of Valencia in Spain. We've been working for about 15 years on wind turbine grid forming control for both HVDC and HVAC integration. Within the promotion project, we've been working in 4 work packages on the development and validation of wind turbine grid forming controllers for direct rectifier connected wind farms, and also for black start and islanding operation. This is an example on how renewable energy can actually contribute to surface restoration after a blackout. Last year in Tenerife, we had a blackout when the system had 40% renewable energy. It took about 9 hours for the full recovery of the system, and system restoration was carried out with gas turbines because the renewable energy there is not black start capable. So if we want to go to the European Green Deal targets of more than 70–80% renewables, not using the renewables for surface restoration is simply not an option. Our main aim is to increase the TRL of grid forming controllers for black start operation, and the first stage is the validation using simulations. To do that, what we have done is first to decide on the functional requirements. Then we will define scenarios for HVAC black start and for HVDC black start, which will be covered by my colleagues of DTU later on. We define test cases for checking the functional requirements on each one of the scenarios. And finally, we will validate the different controllers based on those test cases. And we're going to validate 2 different kinds of controllers. One is a generic control, and we will also validate black boxes coming from vendor-specific controllers. Regarding the functional requirements, we have decided, or we have adapted those requirements from national grid and LRI requirements on black start operations. Some of them are not exactly the same, and some of them are not defined in a very specific way, just to find the limits of the grid forming technical capability. And something important about the requirements is that these requirements right now should be understood not in the way as they are commonly done in the current grid codes, in the sense that now a wind turbine is allowed to trip if some of the voltages or frequency, for example, are outside certain limits. Now the wind turbines are the only grid forming equipment in the system, so they should ensure that they should contribute actively to keep, for example, the voltage and frequency limits within their margins. The scenario we've considered for black start operation is a 400 megawatt wind farm consisting of 50 wind turbines of 8 megawatts each and located 75 kilometers away from the onshore HVAC substation. The connection process starts by a single wind turbine energizing the first string cable, then the rest of the wind turbines of that string. Then we will have enough reactive power to energize the whole array, followed by the rest of the wind turbines. At this stage, the whole system will be operating in an island. And then we will energize the offshore substation, the HVAC export cable, and the onshore substation. So once we have the onshore substation energized, we can actually power up local block loads and finally connect to adjacent islands just to continue with the surface restoration process. The main issues are HVAC cable and transformer energization, response to load transients, and fault response and fault recovery. We have carried out quite a lot of simulations for the different cases, considering sensitivity to number of strings connected, the power that is available, and even a point of wave closing of each one of the breakers. So this is an example of the results for the export cable energization using point of wave, and then you can see here that we have the different voltage that is seen by the offshore collector bus bar, and the currents at the offshore collector bus bar. Is worth noting that the export cable energization is probably the most challenging part of the sequential black start operation. And then these are the results, the distribution of the maximum voltage, current, active power, reactive power, frequency, and rock-off on the wind turbine of 100 different cases with different errors on the pole closing of each one of the breakers. The same has been carried out with different points in the grid, where we can see the maximum and minimum voltages and maximum and minimum current in different buses of the complete system. And we checked that in 99% of the cases we're within the allowable limits, and only in 1 or 2% of the cases the wind turbines would trip due to resonance. We have two more examples. One of them is now a soft start operation, where all the breakers are closed from the wind farm to the onshore substation, and then the voltage is ramped up. These are the wind turbine active power, wind turbine reactive power, wind turbine voltage and frequency. And at t equals 4 seconds, what we have is the block load, where the onshore load is connected. And you can see that during the voltage ramp up and during the block load, all the frequency and voltage is kept within the requirements. Furthermore, we have an example of faults. We have faults during islanding operation in the offshore collector bus, and we have a fault on the 400 kV onshore grid fault once the whole system is energized. So you can see that in both cases the wind turbines react properly, and they are able to recover the system in less than 50 milliseconds after the fault has been cleared. We have carried out detailed verification of both generic and vendor-specific controllers, and the main lessons learned are that with the right requirements, black start operations can be carried out with relatively small modifications to existing converters. That's quite important. Even though in some cases we might need some additional storage in some or all of the wind turbines. Regarding sequential black start, a very detailed study has also been carried out, and is possible, even though in some cases we might have a large overvoltage and overcurrent that in a few percentage of cases can trip the wind turbines. On the other hand, soft start leads to a much faster energization, and there's almost no inrush currents or oscillations. Regarding fault recovery, that's very important, as now the system has to be recovered by the wind turbines themselves after a fault. And also that something that is very important is that the grid forming control has to be very robust to large changes in grid resonance peaks and the interaction with other converters and generators in the same area. The final conclusion is that grid-forming wind power plants can contribute to speed up system restoration. However, we need to align the technology development, the technical requirements, and the business models If you want to have more details on the technical requirements and on the results, we have the deliverable 3.7, which is openly available in the promotion website. Thanks a lot for your attention, and I'll be happy to answer any questions you may have.
Welcome to this presentation on the simulations for HVDC connected offshore wind power plants as part of Work Package 3. My name is Anubhav Jain, and I'm a PhD at DTU Wind Energy working on the black start and islanding capabilities of offshore wind power plants. My project is part of the INODC consortium, and my main role in promotion has been in Work Package 3, working on what is the focus of this presentation. I'll keep the agenda relatively straightforward, starting with a brief description of the model and the controls that we use. Then I'll explain the energization sequence for the hard switching and soft start studies that we have performed, giving also some results. And then finally, I'll conclude with a brief or a preliminary sort of sensitivity analysis that we did to see how different parameters impact the energization transients. So what we have here is 200 kilometer long symmetric monopole HVDC. So it's a two-terminal point-to-point HVDC link. On the left-hand side, you see the offshore MMC, which is connected to the grid-forming wind power plant. So the wind power plant energizes the offshore network, and then the offshore MMC controls the DC link. Then on the right-hand side, you see there is the onshore MMC, which works in an islanding mode. That means it controls the voltage and frequency of onshore DCC. And then we have 30 megawatt block load to demonstrate the black start capabilities of the grid-forming wind power plant. The offshore wind power plant is modeled with partial aggregation. So you have one string with 9 individual wind turbines. The second string is modeled as an aggregate, and then the remaining 32 wind turbines are modeled as one wind turbine. Each wind turbine consists of this structure. So we have the voltage source connected to the filter of the converter, and then we have a wind turbine transformers. Now this is an average model of the grid side converter of the wind turbines, assuming that the DC link is maintained constant by the rotor side converter control. The control of the grid forming wind turbines that we use here is as proposed by University of Strathclyde, which is called the distributed PL based grid forming control. It consists of a standard cascade voltage and current control structure with an additional frequency control loop that uses the PL output as an indication of the frequency deviation. There are also outer controls that are present, but for this study we disable them as everything is working in an islanded mode of operation. So now I'm going to explain the energization sequence. So what different steps are in the hard switching and soft start of offshore network. For the hard switching case, we have the grid forming turbines starting and energizing the offshore PCC, after which the main breaker is closed to energize the transformer and the offshore MMC cells with the PIR in the circuit. After a certain pre-insertion time, this auxiliary breaker is closed to bypass the PIR and then have the whole offshore network energized. The soft start case, this entire circuit is kept connected from the beginning, and the grid forming wind turbines just ramp up the voltage slowly while energizing the entire network in a controlled manner. Once the offshore circuit has been energized, the next stage is that the offshore MMC deblocks to control the DC link voltage of the HVDC link, which is then used to pre-charge the onshore MMC in a controlled manner. Once the onshore MMC cells are pre-charged, it is deblocked to control the voltage and frequency of the onshore PCC, and finally a block load of 30 megawatt is connected to demonstrate the black starting capabilities. Now I'll show you the results for the different energization sequences. Starting with the offshore circuit, on the left is what you see the hard switching case, as is clear from the wind turbine voltages that are 1 per unit from the start. And on the right, you see a soft start case in which the wind turbine voltages are ramped up slowly from 0 to 1 per unit. This is the converter voltage and the converter valve currents and the cell voltages. This waveform shows the DC link of the HVDC cable, and finally at the end what you see is the powers that are delivered by the wind power plant. What is clear from these results is that the charging peaks for hard switching are much higher than the soft start case, and also the soft start allows a faster energization of the entire network. However, this depends on the ramp times and the values of the PIR PIT, for which we have done some sensitivity analysis, the results of which I will show you soon. The next stage is the offshore MMC deblocking to control the HVDC link to its rated 640 kV, and this is associated with the power surge from the wind power plant. Then comes the DC side pre-charging of the onshore MMC, which is opposite to the AC side pre-charging of the offshore MMC. We follow a very simple protocol here, in which first the upper arm of the onshore MMC is pre-charged to its rated values, and then the lower arm is pre-charged to its rated values. Now, as you see here, we didn't have any closed loop control over the valve currents, which can also be implemented for better control over the transients. However, the main aim was to just ensure a low dip in the DC link voltage, and the transients in the offshore MMC valve currents and cell voltages are not uncontrolled. Finally, a 30 megawatt block load is connected, which is associated with a small drop in the HVDC voltage, which is, however, recovered very fast. Now, coming to the sensitivity analysis, first, this is for the hard switching case, in which we choose 3 different PIR values and 3 different PIT values to see how that impacts the energization transients. As you can see, there is a voltage dip at the bypassing of the PIR, and this dip is larger for smaller values of the insertion times and larger PIR values. Also associated with the PIR insertion and bypass, there are peaks, and for the PIR insertion peak, that can be reduced with a higher value of PIR, and for bypass, to reduce the peaks at the PIR bypass, a larger PIT or larger time can be used, which would lead to a smaller peak. One important parameter to study is also the energy dissipated by the PIR during the insertion time. Why this is important? Because it determines the heating and cooling duty cycle of the PIR and also its size on the offshore platform, which can be important because real estate is very costly on the offshore platform. For the soft start case, we tried 3 different ramp times as shown here, and as you can see, even for the fastest ramp of about 0.5 seconds, the charging peaks from the power plant is only 20% of its rated capacity. It shows that the energization is possible while having still a lot of capacity remaining for the wind power plant. This brings me to the conclusion that soft start is more preferred over hard switching case, or would be more preferable. However, to ensure robustness, we need to do more fault studies during the soft start energization sequence, because, for example, resonance could be excited due to the sudden post-fault voltage recovery after the breaker opens. And for hard switching case, to have a better or a more detailed design of the PIR, more statistical simulations like Monte Carlo simulations are needed to cope to ensure that we can deal with the worst case scenario. Finally, the next steps for us are to increase the details of the model of the wind turbines, which mainly deals with the switching model of the grid side converter, and has some sort of roadside converter control to study the wind turbine DC link transients. With this, I would like to thank you for your attention, and if there are any questions, please do not hesitate to contact me. Thank you so much.